Precalc, no outline 1.1. We're finally into the actual chapters of the book, so we're not doing the P pages anymore.
We're into the real stuff.
So we're into the real stuff.
Hey, I caught the meat.
We are recording right now.
That's cool. I've been watching some of this so I can go back.
I heard myself on one of your videos earlier. Hello, future me.
Okay. Today we're going to talk about functions, but before we get into what functions are, we have to do a little background knowledge because we're going to start talking about functions, about where values can be, where they can't be, some kind of restrictions. So let's back up all the way to, I think, even 0.1 and talk about what those numbers are again. We have real numbers. We had real numbers which were broken into real or rational and irrational numbers. And then within there, you had those circles of integers, whole numbers, and then natural numbers. And those are listed here. So therefore, you guys should know those. They're already in your notes. You don't need to necessarily copy them down again. But how we're going to use these today is we are going to use set notation. The book calls it set builder notation. We'll call it set notation or set builder notation. It doesn't matter. Basically, if it's set notation, it's going to use sets. And so, yes, you're going to have those brackets. And so this is how set notation works. They put a bracket, and then they name a variable. So they name a variable. We're going to name it x because a lot of times we use x. Okay? So we're going to say that x, and then we're going to put a line. That line means such that. So the very first thing defines a variable, and now we say such that with some guidelines. And those guidelines can be of any kind of variation, and a lot of times in set notation, we use inequalities. So x such that negative 2 is less than or equal to x, which is less than 3, is the rule. Now when you think of that, that's a span of numbers from negative 2 all the way up to 3. Includes negative 2, but does it include 3? No. Can it be 1.578349? Yeah. So it can be anything in between there. And so what the book says that you need to do is do this. Where, put a comma, where x is within. Okay, back after some difficulties here. Then what they say is that where x is a little e, it's like an e, or a backwards e, but r, and it's a capital R. This means that x is within, it's kind of like the subset thing, the real numbers. The capital R would mean the real numbers, and that's from the table there.
So that means it can't be like a negative?
No, if it is a real number, it can be any number that's real. But we already have a limitation here that it says it's between negative 2 and 3. So what we're going to do is we're going to use the same exact setup for A, B, and C. Now, what I am going to suggest is that I think if I left off this part here and I covered it up, which I can't really do it here, if I cover up the fact that I'm going to call them all real numbers, I think everybody would assume that any number between negative 2 and 3 was implied, because that's what the inequality says. This only needs to be here, I say, if it's less or something different than all real numbers. So if I was only looking for, like in part A, 1, 2, 3, 4, 5, ... means goes on forever, that's different. Because I am not including every number you can think of, right? It's only including those nice numbers. And so if I wanted to set up the set notation, I can do something like G. I'm going to call it G. Such that, what is the restriction on G? What's the restriction? Yeah, it has to be greater than 1. So G is greater than, can it be equal to 1? Okay, greater than or equal to 1. Where G, it can't be all the real numbers, because if I was all the real numbers, then I could be 1.5 and 1.25. I have to be a certain type of real number. I could say whole numbers. I could even say integers. But I think there's even a more selective group that it could be closer to. Look at our list of options. And natural numbers. Notice that when I said real or natural, or I'm going to use whole or integers, I'm going to use a capital letter. Natural numbers are the way you learn to count. How do you learn to count? Basically, yes, positive, nice ones. 1, 2, 3, 4. 0 is the whole numbers. Now, do you guys see how I could technically use the whole numbers or integers here? Because those actually include 1, 2, 3, 4, 5. And since I'm limiting or talking about it being greater than or equal to 1, I can use those. What about x is less than or equal to -3? So what variable am I using? I have to use x because x is part of that inequality. Such that, what's the restriction? It says it right there, guys. X is less than or equal to -3. Now, is there any other restrictions? So, what kind of numbers could you assume are in there? Anything you want, right? That fulfills that inequality. So that would include decimals, fractions, negative numbers, obviously. Nothing positive, because you've already stated that. I'm going to say that's enough. You don't need to state that x is a real number, because we're going to say it's implied. If you want to put a comma and say x is on the real numbers, go right ahead. Okay, I'm trying to simplify this a little bit. We're going to assume if you don't state that it's on any particular numbers, type of real number, it's going to apply it's a real number. It could be any. C is an interesting one because it has to be multiples of pi. Someone give me a multiple of pi. 6.28, but that actually would be what in terms of pi itself?
Oh, pi squared.
2 pi.
2 pi, yeah. No, it wouldn't be squared. That'd be 9.
Give me another one. 3 pi, 4 pi, 8 pi, 100 pi, -2 pi. What about 0 pi? Is that a multiple of pi? Technically, yeah. So, this one's interesting because, again, there's no variable listed. So you got to call it something. Someone give me a variable. Q, I heard. Okay. Q, such that here's the thing. Q is a multiple of pi. So you know it has to have pi in there, right? But we could have 1 pi, 2 pi, 3 pi, -2 pi, 0 pi. It's changing. It can change, but it has to have a pi to it. And so this is the complicated part. The complicated part says I need to introduce another variable, n. That's it. I'll redraw it. pi. The thing is that the restriction then falls on n, because n has to be a special number. So now I can go and say, where n is in what? N has to be what to be a 1 pi, 2 pi, 3 pi, 0 pi, negative 1 pi, negative 2 pi? An integer. So going to our list, integer is what? Capital letter. So n is on the z. Okay? So Q, such that n pi is n pi, where n can be any integer it wants to be. Now, I personally don't necessarily want to use set notation if I'm covering a span. As in, look at our examples there. They're inequalities. They go from here to there. And so I'd rather use something called interval notation. Interval notation looks a lot like just a regular, standard old point. So you kind of have that x comma y type feel to it. But it's not a point. It's actually telling us what values it can and cannot be. Because you will use different things. Sometimes you'll use a bracket that has more of those hooks on it, like so. Or you will use parentheses, which don't have the hooks, because brackets mean that the point is included, and parentheses means it's not included at the end. Now, we will also use positive infinity and negative infinity in interval notation. We could technically do this in with our inequalities as well, but it's just easier to say, like in part B, a is greater than or equal to negative 3. We just know that it's going to go up to positive infinity, and you can find any number you want. We don't need to write that it's less than negative infinity. Now, also remember, you can't point to something and say that's infinite. Because as soon as you find something that's infinite, I'm going to point to it or give you one more than that. So if you give me an infinite number, you're going to call is infinite, I'll give you one little bit bigger. And then you can give me a bigger number. And back and forth, we'll never actually be there. And since you can't be there, infinities are never included and will always have a parentheses. Okay? So, looking at A. Y is from negative 4, is less than or equal to y, is less than negative 1.
There's a y in front of it?
No. Just negative 4, less than or equal to y, is less than negative 1. Now, for some of these, it might be helpful to draw the graph of this. And if I had to draw a graph on a number line, wouldn't you guys say that would be negative 4, negative 1? You would have what kind of dots? Closed at negative 4 and open at negative 1, yeah? And then I'd shade the middle. Check a point, shade, check 0. Does 0 make that true? Yeah, so shade in the middle. That's what I'm going to see, because that's what the inequality is. Interval notation just uses those endpoints, and then you just have to look at that graph or look at your inequality and say, is negative 4 included? Yes. Bracket. Negative 1 included? No. Parentheses. You are now done. That is interval notation. Interval notation says the numbers for y will be between negative 4 and negative 1, and negative 4 is included. So, try part B. So, for part B, if I had to graph this, it'd be a negative 3, it's a closed dot, and shaded to the right. Everybody should have that, right?
I thought that was
Explain.
what?
You good? Okay. So, now, what that means is that negative 3 is my left bound. It stops going to the left at negative 3. But when it goes to the right, does it ever stop?
No, it's infinite.
So it's going to go to positive infinity. You don't necessarily need the positive there. But the thing is, can you ever actually achieve positive infinity?
Yes.
No. So therefore, since you can never officially be there, it's a parentheses. Can you actually be at -3 though?
Yes.
So therefore, it's a closed bracket again. Now,
can never achieve it.
you can never get to infinity. You can't be there.
Is it possible to have negative?
The next one, I ask you to graph this. And so when you do, you realize that, oh, -2 should be on the left, but 9 should be on the right. This is another reason why I like to put a little bit of a graph to this, is that I can order things in the right place. Either way, both of these dots will be open. And if I go to the -2 version, it says x is less than -2. Oh, that's going to the left. X is greater than 9 goes to the right. This is an OR. So if I had a game, and the game stated that you had to be a Notre Dame student, or you just had to be under 18 to play.
You can be both,
You can be both.
but you can't be both.
It says, could everybody in this room play a game?
No, then I couldn't. You said you have to be under 18.
I said, or a Notre Dame student. So could all of you play this game?
Yeah.
Yes.
But that is more complicated.
Could somebody at Franklin play my game?
Yes.
If they were under
If they're
18.
If they're under 18.
I got you. All of them.
So everybody at the middle school should be able to play my game. Could I play the game?
No.
Why?
You don't have to score.
Because I am not in either or of those camps.
I have a question.
Yes.
If you're relating this to the graph, that would mean that they would be in the middle area. But they're not.
No. The middle area would be where it's not the or. The answer lies to the left or to the right. It does not lie in the middle.
So what is in the
So
middle
we
then?
write
The
negative.
middle is the and.
But okay. So that would be the people that are both then?
Well, in this case, this one does not. You can't, guys. Listen. You can't. This one doesn't work for an and. Now, if it can be an and, if I said you had to be a Notre Dame student and you had to be under 18, that might actually eliminate some kids in this room because they are 18 or older. Therefore, they can't play my game. Because, they don't fit into both categories. An and means where they overlap in people that are in both groups.
Or is either
Or is it either people in this one or that one? If you fulfill one of the requirements, you're good to go. So, I use this to help me figure out that negative infinity is on the far left. -2 is next. 9 and positive infinity. Can I ever be at those infinities again? So therefore, both of these will get parentheses on the very far ends. But can I be at -2? No. Can I be at 9? No. At this point, I have two different set notations. Or not, interval notation, sorry. We dealt with sets before. It just deals exactly the same way. I've got a set of numbers from -2 to negative infinity, and another set of numbers from 9 to positive infinity. If I can be in either one of these to be the solution overall is the what of these two groups. It's one of the symbols we used in that set in our set notation stuff. The U, or union, between the two groups, which means all the members between the groups would be solutions. An and statement would be this and that, and the only people or things that would work is the ones that are in both of the sets, and you would use the intersection.
Is this like from the first day of
Moving on from notations, I would like to also talk about now what's a relation. So we got to call what's a relation, what's a function. Most of us can understand that a relation, a function, is a type of relation. But here's the thing, not all functions, or all relations are functions. Does anybody recall what a relation is? A mathematical relation. A mathematical relation is just some kind of connection from inputs to outputs. There's a rule, there's some kind of established, ordered pair. Those can be relations. A function, guys, takes it a little bit further. A function sits back and says, hey, if you want to be a function, it means that every output has exactly one input. Every output has exactly one input. Right? Wait, did I say it wrong? Hold on. That didn't sound right. Now that I'm saying that again. Sorry, it's the other way around. Every output has exactly,
Every input has one output.
yeah, there's exactly one output for every input. Wow. The third time's a charm in the classes that you start messing things up. So, sorry, rewrite that, erase it, erase the video stuff. Okay.
Every input has one output.
There's exactly one output for every input. Go. So, again, I like to equate this as going down to my favorite soda machine. And I like Diet Dew. I know it's bad for me, okay? Don't have to tell me. Now, if I go put my money in the machine and I hit the Diet Dew button, what should come out? A Diet Dew. If I push that button again, another Diet Dew should fall out. And if I keep pushing that button indefinitely, hopefully, as it should, a new Diet Dew should fall out. Now, if I push that button, and I get a regular Dew, I'm upset. That means the machine is not functioning correctly. Because every time I push the button input for a certain button, that same soda should be coming out. Now, sometimes in high traffic areas, they put a machine that has multiple, right? Multiple inputs that go to the same type of soda. So that's okay. It's a different button, which means it's a different input that can go to the same output. Perfectly fine. So a lot of times, to do this, to tell if it's a function or not, we create a mapping. This is called a mapping. And then you can draw lines that connect inputs to outputs. Clearly you can see that's a relationship. Now, is this relationship a function?
Yes.
Does every input go to a single output?
No.
No, I thought you said every output has a single input.
No, remember I changed that.
Every input has exactly one output.
Every output has a single, wow.
You said every output.
There's exactly one output for every input. So that means, that means when I put something in, it needs to go to the same thing every time. 2 and 3 there, both go to an 8, yes? That's okay. Because every time I put a 2 in, where is it going? 8. Doesn't matter if I put it in 1,000,000 times. That 1,000,000th and first time, it's going to 8 again. That's okay. It's functioning correctly. That's a function. Yes. I can also take these points and I could graph them below here, which these are not the points. But what we can do is we can do the vertical line test. You guys should remember that. That says that if I have a graph of some sort, plot points or whatever, if I draw vertical lines through here, my vertical line shall only intercept the graph at most once to be a function. Any more than that, it's not a function. So, part A. This one's an interesting one. It says the input value X is an area code. The output value Y is the phone number in that area code. Is that a function? Yes or no? Jake, what's your area code? 920. Ish, what's your area code? 920. Mine's 920. Pretty much, probably all of us right here are 920, right?
That's not true. That's false.
Not wheels.
False.
So, I said most. I said most.
1847. That's false.
Okay.
1,844.
Okay, guys, listen. According to this
Don't die down.
relationship, it says that if I pick up the phone and I dial 920, I could get Jake's number. But I could also pick up the phone, hit 920, and get Ish's number or mine. No, I do not want your number. But here's the thing, guys. What it's saying, according to this rule, is that the same input is allowing me to go to many, many different outputs. Is this a function?
No.
0769.
Okay? So this is not a function. Is 3b a function?
No.
The answer?
No.
No, because
Yeah, we gotta go to 5.
both 5s go to different outputs. They need to go to the same output, so no. What about 3c? I can draw vertical lines on this all day long while I hit the graph more than once.
No.
So therefore,
It's a function.
it is a function.
Oh.
3D. Does anybody know what that is?
Those vertical lines.
3-dimensional.
It's not three-dimensional.
Yeah, that's what 3D was.
I said, what is the...
Wouldn't you want to get y by itself?
You could get y by itself, but what is it?
The function.
No, what is that equation? What is the equation in 3D?
The line.
It's a line.
Is that what you mean?
Yes. Now everybody with their hands, show me a line. Go. Okay. There are actually about 3 people in this room.
Show me the board again.
3 or 4 now, more people, are giving me examples of lines that are functions, and then there's lines that are not functions. Guys? The ones that's not a function would have to be a vertical line. Because a vertical line does not pass the vertical line test. But any other line would have a slope which would pass the vertical line test. In this case, the only time you ever have a vertical line is an x equals. So therefore, that's not an x equals. D is a function. Last things I want to talk about before the end here. Function notation. Function notation, guys. Function notation is this thing. What is this called? F of x. H of m. G of n. Right? All of those are function notations. And when I say function notation, that means it's a function we call f made up of x's. It's a function h made up of m's. So you may have 2m squared plus 2m plus 3. It's just the variable itself in that function is an m. And a g of n means that the variable is an n. Right? Tomorrow we're going to go into evaluating those, as you can see. But today we're going to finish up with independent variable and dependent variable. The independent variable is what? The one that changes. Yeah, the variable that changes. We would use the input for that, because we input the variable we want. The independent variable is the one that we're allowed to control. And sometimes we call that the domain, which is another word that we are going to define later on. And a lot of times in equations, we let that one be the x variable. The dependent variable, we don't get the change because that is the output. It's the range, and a lot of times we call that the y. The dependent variable depends on what you put into the function. We sometimes try to control the outcome by controlling the inputs. That's how we control that. Okay? Any questions? Homework? Page 9, 1 through 27, odds. Have a great day.